So what we just found in the last one is that if a polynomial f of x is divided by x minus c, then the remainder is the number f of c. Now we can only do this when we're dividing by x minus some number. That's fine. That's a very common thing that we want to do. So we can't do it always in general if we want to divide by x squared plus 8 or something like that. It's not the same thing. But if we divide some f of x by x minus c, then all we need to do is plug in the c into the function, and we can get our remainder. And that's the remainder theorem. And it's a very useful tool. So let's look at this one. Here's a function, and I want to divide it by x plus 2 and find out what the remainder is. Now, I don't want to have to divide that whole thing. That would be a long division. If I just want to find the remainder, then I look at x plus 2 and I say x plus 2 is actually x minus negative 2. So that's the value I want to put in, negative 2. So I'm going to do f of negative 2. Well, that would be 3 times negative 2 to the 5th plus 5 times negative 2 to the 4th minus 4 times negative 2 to the 3rd plus 7 times negative 2 plus 3. All right, that's negative 96 plus 80 plus 32 minus 14 plus 3. Go ahead and do that, and that's 5. So knowing that f of 2 is 5 means the remainder would be 5 if I did the whole polynomial division. Now, why is that important? Well, what I found is specifically the remainder wasn't 0. So I know that this x plus 2 did not divide cleanly into that polynomial. In fact, that x plus 2 is not a factor of this polynomial. And negative 2 is not a number that makes that polynomial equal to 0, which is part of what I'm really going for here. And that's where I come into roots. If f of x is a polynomial, solutions to f of x equals 0 are called roots or zeros of f of x. So that's really what I'm trying to find. I'm trying to find numbers that I plug in and I get 0 out of the function. But that's the same thing as getting 0 from the division of x minus that number that I put in. Okay, so here's how we're connecting it. F of x was x cubed minus 7x plus 6 in the earlier example. We saw that plugging 1 in gave us 0, which meant the remainder was 0 if we divided. That makes x equal to 1 a root of f of x. And that means x minus 1 is a factor of f of x. So we have a three-pronged connection here. The number c is a root or 0 of the polynomial whenever x minus c is a factor of f of x. And that would connect to the polynomial division, meaning you're getting a remainder of 0. So the number is a root when x minus that number is a factor and the remainder is 0. So c would be a root, x minus c would be a factor, and this is all connected to a remainder of 0 from the polynomial division. These things, remember those things as a nice triplet there. The number is a root when x minus that number is a factor and the remainder equals 0 from the polynomial division. All right, so we found for that f of x as x cubed minus 7x plus 6, we found that 1 was a root. But how many roots are there? Remember, we did this f of x equals 0, solving that for quadratics quite thoroughly. that was when we were doing roots of a quadratic, and we found there were always 2. So what can we say now? Well, let's take a look at f of x. We saw that we could, if we divided x cubed minus 7x plus 6, then we would get this. But this is just a nice quadratic. We could actually factor it and get x minus 2 times x plus 3. That's a pretty simple factoring of x squared plus x minus 6. That shows us, so now let's take a look. That shows us that x equals 1, we already knew, would solve this, make it equal to 0. And x equals 2 would work, and x equals minus 3 would work. So we actually got 3 distinct, because they were different, roots. Now, it's not surprising that we got 3 roots. Now, they didn't have to be distinct, but it's not surprising that we got 3 roots. We're going to see because we did a cubic here. When we did a polynomial, we got, when we did a quadratic, we got 2. And when we solved a linear equation, as long as there weren't infinitely many or no solutions, we got 1. So we're getting a number of roots that matches the degree of the polynomial. And that is one of the biggest things we'll look at here, called the fundamental theorem of algebra. A polynomial of degree n has n roots. Again, we have to count the multiple roots separately, as we did with the quadratic. So it has at most n distinct roots. So this cubic here did have 3 distinct roots. That's the most it can have. So we could have had 2 distinct roots or 1 distinct root as well, but it had to have 3 roots in total. And that's a beautiful result, that as soon as we see a polynomial, as soon as we see and we can recognize its degree, then we know exactly how many roots that polynomial has if we do f of x equals 0. Big result. Fundamental theorem of algebra.